In this video, we are going to answer the question, what is earthwork optimization? And talk a little bit about the processes and workflows for using Softtree Technical Systems RoadEng with Softtree Optimal tool in order to be able to optimize the earthworks for your project. So if you are designing roads in complicated terrain, one of the biggest costs is of earthworks, that subgrade that the road is built upon. And in this video, we're going to learn how you can optimize that in two different ways. The first of the earthwork optimization tools in the software that we're going to look at is called Path Explorer AI. This is a generative design tool that will allow you to answer the question, where do we put the road? If you have some flexibility in your horizontal alignment, Path Explorer is a great solution to jumpstart the design process by leveraging the power of AI to evaluate hundreds of millions of options in order to determine the best location for your road. From there, the second key optimization tool that we'll take a look at in this video is called Profile Optimization, which then goes even further and more detailed into the process of how do we optimize cost. Specifically, how do we optimize the cutting and filling cost of those most expensive parts of the road's construction, the subgrade. So in this video, we're going to take a look at both of these tools and really understand how they can be used together to lead to massive reductions in subgrade earthwork costs, as well as design time. So let's start by taking a look at Path Explorer and understanding a little bit more about what it does. So Path Explorer is located inside the terrain module of RoadEng, and it is our AI tool for route optimization. It looks and considers 2 points, point A and point B, and is going to dynamically search that 3D space to find cost-effective alignments between them. In a future version that's releasing sometime in 2025, this functionality is actually going to be expanded to full networks. So please make sure to check back the space. That exciting update is coming. So as we look between points A and points B, we're going to consider some really key design factors in order to help generate our designs. That's things like road width, the grade, side slopes, your minimum maximum vertical offsets, minimum horizontal curvature to meet your design specifications, as well as you have the ability to add in other geometric constraints, such as minimizing stream crossings, avoidance areas, so on and so forth. So Path Explorer, although it looked like it was creating a line on the map, it's not. It's doing a very robust 3D problem that's road specific. So as you can see here in the picture, Path Explorer is solving full three-dimensional road design, but using a simplified cross-section. In order to do this, we look at only a few elements of the road in order to get the best approximations of earthworks and being able to solve the problem in a matter of minutes. So we look at things like the road width, your cut and fill slopes, and as well as we look at sort of three buckets of cost, whether that's your cut cost, your fill cost, as well as your surfacing cost. So this is kind of Path Explorer. Let's pause this video, jump into the software. We'll take a look at how it runs. Okay, so this are the desktop icons for RoadEng. We're going to start by opening RoadEng Terrain module. So the Terrain module is the module where we handle our spatial data. And for the purpose of this demonstration, we're actually going to start with it totally blank. So here we're going to load in some LiDAR tiles. I've got 4 LiDAR tiles. I'm just dragging and dropping them into the software. Lots of options, but keeping this nice and simple, we're just going to insert them. RoadEng handles a fair bit of data and is able to very quickly generate a 3-dimensional model as well as your contours. So here I'm just generating a tin, and you can see here in our 3D, we've created a surface. Now this surface only has about 2.6 million points in it, but we have gone and created a surface. So Path Explorer is really quite amazing in the sense that we can then figure out how to go from point A to point B. We'll bring in another feature here. This is our prelim road. It is coming in the format of a shapefile. Again, I'm just dragging, dropping into the project. You can see our shapefile, and that's going to represent our start and our endpoints. Now, Path Explorer is really useful for considering a bunch of different elements, whether, as I mentioned, your road width, your slopes, all of the sort of road properties. But it's also really useful for making sure that we can minimize crossing streams or other constraints like that. So one of the features we've got here inside the terrain module is the ability to quickly run streams and ponds. And I'm here just going to run that on our model. Perfect. So we've just determined where the surface water is. And now with our preliminary road feature selected that represents the start and endpoint of where we want to go, we can now move ahead into Path Explorer. So up optimization ribbon, hit Path Explorer, and now we're going to set some parameters. We can ask Path Explorer to give us a particular number of generated design options. So in this case, we can ask it for 5. We can ask it for a particular minimum horizontal curve radius, a particular width, and again, remember that this includes things like ditches within the width because we've simplified our cross-section. We can define our max cut, max fill, our costs, our grades, and our slopes. And we can also press this construction zone button here, and we can include those areas of different cost. For example, if we select polylines and select our streams and creeks layer, we can now give it a crossing cost for any time we're going to cross one of these streams. That could be representative of the cost of improving the different types of materials we're working with there, or a culvert location. If you had a major river crossing, you could certainly add that in as well. And with that, simple changes, some simple construction zones, we hit OK, and Path Explorer now is going to go look to solve the complicated problem of where do you put a road on this landscape that minimizes cut, minimizes fill. Perfect. It has already found us 5 paths that meet all of our criteria, and it's going to continue looking for better alternatives. We can press cancel at this point or at any point once it's found some paths to accept the current solutions. And of course, it's always better to let it continue its search until it thinks it is unable to find better alternatives. Okay, there it is, the message we want. It now says it's unlikely to improve further. We hit cancel. So what Path Explorer has now done, it's gone and searched this terrain to understand the best locations for our road to get from this point, the start point, to the end point across this terrain while minimizing crossings. It's meeting our horizontal curvature constraints, our grade constraints, and looking again to minimize cut and fill. You can quickly see which one of these 5 alignment options is our best option by going select features by name, and they are ranked in order with a very, very rough cost attached to them. So this one here, this X path 114, now shown in magenta, is our best option. We're going to come back to this example and show you how to use vertical optimization on it. Before we can go and do a vertical optimization on it, let's learn a little bit more about what that next step of earthwork optimization looks like. So what is vertical optimization? Well, unlike Path Explorer, which is an AI-based process, vertical optimization is just a whole bunch of really, really fancy math, and it's used to determine the lowest cost alignment, which satisfies the different constraints and standards. Vertical optimization can be a lot more detailed than path exploration because here we're able to include a full detailed cross-section. We're able to include a lot more elements tied into the construction process as well as the materials process that allows us to get a much more realistic picture of how we might actually construct the road, whether that's including different materials in our cross-section to represent how we're actually going to build it, or the materials in our ground that we're going to leverage and understand where they go to and how they work. So vertical optimization, again, very fancy math that's going to handle all of that. It's going to turn the next phase of road design into a semi-automated process. It is going to give you a true minimization of earthwork costs. And it's really a process that's suitable for new builds as well as realignments. So for projects that have no ability to move horizontally, it is still very much applicable as we're looking just at the vertical. Okay, so what is vertical optimization? How do we explain this? So imagine you have a ground profile. Then you're going to go, and as a designer or an engineer, you're going to create a vertical alignment on that ground surface. You're going to be looking at your grades and your cuts and your fills and trying to balance it manually. Well, what vertical optimization does is it takes that and turns it into an automated process where the computer is going to look at the constraints and look at how do we minimize those little bits of cut and fill. And across an alignment, all those small changes in the profile, the little vertical adjustments, they add up dramatically. We're looking at somewhere in the neighborhood of 10 to 30% reduction in subgrade costs by leveraging vertical optimization. So really, how does it work? We take the existing ground, we take that preliminary horizontal alignment that Path Explorer has given us, we set up our cross-section geometry, input costs and ground types, and add in constraints. These can be things like your minimum maximum grades, design speeds, and then it goes into the optimization engine, and out comes three key things. First of all is your vertical alignment. It's going to give you that, including all of your curved geometry. It's going to give you a dollar cost for that alignment and a very interesting earthwork movement schedule. So really, the big benefits here of using vertical optimization: reduced subgrade construction costs, an ability to automatically balance your mass haul, huge reduction in engineering time spent, an ability to track and report your material movement, quantitatively being able to compare alignments based on their construction costs. So you can iterate different options, check out different K values really quickly, do some what we like to call optioneering. And then you can also very quickly check the feasibility of preliminary designs. So as a whole, optimization is going to lead to some very dramatic project cost reductions, especially on your subgrade. You've got that balanced mass haul, you're going to save time, and you're going to be able to track and report your material movement. Now let's go back into the software, finish checking out that example, and see what it looks like as we take it through to the vertical optimization process. Okay, so here's our example. We've got that lowest cost path still selected. I did go and save it. That's pretty much the only thing that's been done in the background. And now let's head into the location module and turn this alignment into a full geometric alignment with a detailed cross-section ready for vertical optimization. So here we just new file. We're going to select our topo surface that we created. It's got our X path selected. Okay, and now we are ready to get going with optimization. So if you're new to RoadEng, quick primer, all the windows are dynamic and connected with each other. A change in one, you can see my cursor. They are interrelated and connected. The cross-section windows, they've got a profile window. They're all controlled down here, but all the windows are connected. So the very first step here would be to set up our typical cross-section template. For this project, our default one actually suits my needs quite perfectly, but you can make changes, and as well, you can also explore what the cross-section template looks like here in the template editor. So once you're happy you've set up a template, which is essentially like a fillable form, you can adjust it, which actually is a good reminder. Let's make our road a little bit wider to be a little bit more indicative of what we actually created. Okay, step one. Step two, Path Explorer comes in as a polyline. We're going to turn it through another fancy math tool into a proper alignment with curves. Step one is I'm running the polyline to alignment tool. Perfect, it's done. And now we're ready for vertical optimization. There is a lot more complexity we could add. We could define the materials in the ground. We could define the materials that are needed in our cross-section. We could also define our borrow and waste sites, or where we're getting our material or where we're spoiling our material to. But for the simple purposes of demonstrating how this works, we are simply just going to go here and set up our optimization to assume that we're just going to leverage the material in the ground. Vertical optimization works by sampling our alignment at particular stations. So if we did a 5-meter spacing, we can control the offset as well as the band. We're going to define our constraints for our road. So we've got an example of our rural road here has got some higher grade constraints. So we can implement these. You can also set constraints by different ranges. One interesting element to know that we have here is what type of optimization it's solving. So we have one called curves fast. This is going to allow curves to go back to back against each other. It is the fastest solving optimization, and if you're just looking for feasibility, this is often a really great place to start. We also have curves and tangents, variable curves and tangents, and an ability where you yourself as the user can set the IPs, and it's going to optimize based on those. So a bunch of options here. For the purposes of this quick introductory video, we're going to leverage curves fast. We can add control points. We can do them start of alignment, end of alignment. We can do grade constraints as well. So you can have, if you're working in, for example, a wind farm project and you have a turbine site, you're going to want a very specific grade as you come into that. Similarly, if you've got an intersection to cross through, you're going to want grade constraints to make sure you tie in appropriately to those. A lot more options as well here in the vertical dialog pits, so controlling your borrow waste sites. Unit costs, this is the foundation of optimization. It is a cost reduction tool. So right now in my project, I have one material. I'm just looking to minimize cutting and filling. I can set my excavation and embankment costs, as well as my haul costs. So this is to represent the different material movement types, whether that is a scraper, a dozer, a truck. You can put those here. And then we have additional constraints that you can use. But we're going to hit process, hit OK, and we are going to let this run. So optimization is not instantaneous, but it is quite quick. We're going to pause the video, come back once it's solved, probably in about 5 minutes from now. Okay, it was really fast. It's telling us that a profile has been found. It is giving us a warning that we do have a short curve. And it's telling us that we needed to have a pit because we've got some different material that is unused. But yeah, very quickly, we have gone from not having a profile on our road to having our profile. And you can see here by the mass haul, it is very close to balancing. Yeah, 167 cubic meters. So within a matter of 19 minutes, we've gone through an introductory PowerPoint. We have created an initial generative alignment design using Path Explorer AI, and now we've been able to really quickly optimize that design even further by adjusting the vertical. We can get all the different volumes for this particular project and outputs here in RoadEng. You can also send this out to another design software if you're working with one. So yeah, a lot of options. So here we were able to go and generate the volumes for our alignment, which are very, very near to balanced. About 6,000 cubic meters of cut and fill happening in the project. So that's a quick look at answering the question, what is Earthwork optimization, leveraging Softtree's RoadEng software. I hope this video was helpful. If you have any questions, please reach out.